Welcome to this session. In this session, we will be exploring the calibration process in Davis software and learning how to record flame images effectively. We will also briefly explain the importance of various components used during this process and analyze their impact on the resulting images. By the end of this session, you will have a comprehensive understanding of how calibration works and how each component contributes to capturing high quality and meaningful data. For recording the high speed chemiluminescence images, we are going to use the Davis software. So, when you open the Davis software, this is how it looks initially. First, we need to add all the important components inside the software. So the key components here are camera, a PTU, and an image intensifier, which is nothing but IRO. As a first step, we need to click on this setup icon as I'm highlighting here. Once you click on setup icon, the device list will appear to be empty. Here we will be adding all the components necessary for our experimental demonstration. To do that, click on the add symbol as I'm pointing out here. Once you press the add symbol, you will see a add device window. So a predefined list of components within the software will appear in this add device window. For our demonstration, we need to add a camera, a PTU, and an image intensifier. So we have to add one by one and then click OK. Once we added all the required components, the interface will look like this. Next, we need to select the devices icon and then press initialize symbol. This step allows the software to detect all the components for controlling each of them from the software itself. After pressing initialization symbol, we can verify whether the software has detected all the components or not. If everything shows OK as shown here, we are good to proceed. Finally, press exit to complete the initialization setup. Now let's record the calibration plate, which is already positioned inside the center of the combustor. To start recording the calibration plate, we need to create a new project inside the Davis software. For this reason, we have to press this new icon as I am showing here. Once we click the new icon, you will be prompted to select the type of project. Since we are going to record only OH chemiluminescence imaging, select imaging under the type of project and then press OK. Once we click OK, we will be taken to the imaging project workspace. This is where all of our recorded files will be stored. Next, click on the recording icon to enter the adjustment window for camera and IRO. Here we can fine tune the settings for the camera and the image intensifier as shown here. The exposure time of the camera can be adjusted based on the respective lighting conditions for individual experiments. Since we are recording the calibration plate, we can set the exposure slightly higher as it is a static object, and here we can change the number of images that has supposed to be recorded for individual cases. You can also modify the image rate of the camera by selecting the timing option, which is measured in frames per second, and here it is shown as kilohertz. To allow the camera to capture more light, you can reduce this frame rate. Lowering the frame rate increases the exposure time for each frame, which enhances the visibility of low intensity signals. Additionally, we can also adjust the intensifier settings to clearly visualize the calibration plate. To brief the settings inside the intensifier, gain is nothing but a multiplier of the incident light signal, and gate is nothing but exposure time for the IRO. Once both of this option is adjusted for the better visualization of the calibration plate, press recording tab to get to the recording option. Once everything is configured properly for capturing the calibration images, press record in the recording tab. After completing the recording for the predefined number of images, which is set to the camera by the software, we can save the file by clicking the save icon, and once it is saved, press the exit option. Once we exit from the recording window, we can see the recorded calibration plate file, which is added inside our project folder in the Davis software. Now that we have taken the calibration image, let's apply the calibration for the upcoming image recordings. For this reason, we need to open the same project which the calibration plate was once saved. Once it is opened, locate this calibration icon and click on it. Here we see a multiple type of calibration in this window. For our demonstration purpose, we have used only one camera and a single coordinate system. Once you enable the option, press next. Next, you will see a list of calibration plates from this particular drop-down menu. Choose the one you are currently using for your experiment. This allows the software to know the predefined dimensions of the calibration plate for references. As shown earlier, the calibration plate contains a equidistant dots which are already encoded in particular 106-10 calibration plate, which is chosen in this window. Now we need to import the recorded calibration plate image for comparing with the already predefined dimensions in the software. For that, Click the file icon to locate the saved file of the calibration plate. Once you locate it, select that particular file and then press open. You will now see the loaded calibration plate image displayed on your screen. Once you are ensured about the proper calibration image, press next option. Next, we need to define the origin of the image field by marking three key positions, which is 0, 0, x, 0 and 0, y. To do this, click on all camera/views. For demonstration purposes, I will mark the center of the calibration plate, but you can choose any convenient positions. Once the points are properly marked on the dots, we can press next. Here, press start search option. The software will now search for the remaining dots locations on the calibration plate. This step is crucial as the software uses the predefined dot distances and positions to detect the alignment of the camera and the focal plane. Once the software searched all the pixels in the calibration plate image, you will notice that software successfully detects almost all the dots on the calibration plate. Once you confirm that, we can click next. Now press the start calibration option. Once the calibration process is finished, press exit. Now the calibration process is complete. We can remove the calibration plate from the combustor and prepare it for the combustion experiment. Now we will conduct a series of experiments to explore the significance of key components such as IRO, bandpass filter and high-speed camera. To demonstrate their importance, we will showcase a sequence of experimental videos featuring different combination of these components. Let's begin with a regular DSLR imaging. This setup captures all the signals emitted from the flame. This also includes the entire visible range of the chemiluminescence signals. While this provides a comprehensive view of the flame, but our primary focus is on capturing a specific chemiluminescence signal, particularly OH and CH star signals. These signals are critical for understanding the combustion processes. And another important thing we can observe from the flame is that it exhibits significant oscillations, which makes it more dynamic in nature. However, this DSLR operating at a frame rate of 60 frames per second, it becomes evident that this speed is insufficient to fully capture the intricate dynamics of the film. This limited frame rate results in loss of critical details, especially in fast changing phenomena. This highlights the need for high speed imaging. Now, let's navigate back to the recording option in the Davis software to access the recording window for the next stages of experiments. Unlike the calibration plate, which is static and predictable in nature, the flame is highly dynamic. Flame is highly dynamic. This means we need to adjust the camera settings to capture these fast changing phenomena accurately. Specifically, we will use a lower exposure time or a higher frame rates. For these experiments, the camera is set at a constant frame rate of 3 kHz. This means the camera can capture 3000 frames per second. This enables us to observe even the most rapid changes in the flame behavior. For this demonstration purpose, we will record around 100 images for each experimental conditions. In this session, we will also perform a series of experiments under the following configurations, that is without IRO and bandpass filter. Second, without IRO but with bandpass filter. Third is with IRO but without bandpass filter. And finally, with IRO and with bandpass filter. These series of experiments will help us to understand the importance of each components for recording the chemiluminescence signal. Now, let's begin with the recording setup without IRO and without a bandpass filter. This means there is no filter is attached in front of the UV lens. In this configuration, the recorded video of the flame displays signals similar to those captured by the DSLR image. However, you will notice a significant reduction in signal intensity. This decrease in intensity occurs because we have increased the camera frame rates. This allows to capture more frames per second. Even though this helps in capturing the dynamic behavior of the flame more precisely, but this higher frame rate results in shorter exposure times. thereby reducing the amount of light goes into the camera, and this intensity of the flame is on par with the noise level of the image. So it is hard to distinguish between a background noise and the flame signals. Now for the second test, we will introduce a bandpass filter while still excluding the IRO. By using this bandpass filter, we allow only signals with a specific wavelength range passes through the UV lens. In this case, we are using a 310 nanometer wavelength which specifically isolate a OH star chemiluminescence signals. However, as you can see in the video, the results are completely dark. This aligns with our earlier observation, that is without a bandpass filter and without an IRO. In general, the intensity of the OH signals from the flame is inherently very low and cannot be effectively captured without a signal amplifier. By adding the bandpass filter, we have further reduced the already faint signal, allowing only a narrow band of wavelength to pass through the UV lens. This demonstrates the challenges of capturing a specific chemiluminescence signals and highlights the necessary of the component like IRO to amplify these low intensity emissions. Here in this experiment, we have used a IRO but without a bandpass filter. In this setup, we can clearly see the flame with excellent contrast compared to the earlier experiments. This is completely similar to the DSLR video which we captured earlier. The key difference here is the intensity of the flame is significantly higher. This is possible because we have slightly increased the gain from the intensifier settings. However, these images still contain all the wavelengths present in the flame. But for our specific requirement, we need only OH star chemiluminescence signals. As we discussed in the theory session, signals in the UV range like OH chemiluminescence carry a higher energy compared to those in the visible range. This is why we focus on capturing the OH signals from the flame, and these signals are directly proportional to the local heat release rate of the flame. By isolating and analyzing these signals, we can gain a valuable insights in the combustion processes, and we can also understand the dynamics of the flame. As a final experiment, we have performed flame chemiluminescence imaging with IRO and with a bandpass filter. For this setup, we have configured the IRO with proper gain and gate values according to our flame intensity. As we have used a bandpass filter of 310 nanometer wavelength, we can surely tell that the filter allowed only a OH chemiluminescence signals to the camera through IRO and UV lens. This specific combination is designed to amplify the incoming signals and make them strong enough to be detected by the camera. As a result, we can now clearly see the images, including the OH chemiluminescence signals from the flame. The UV signals, which were previously undetectable due to their low intensity, are now effectively captured because of the signal intensification provided by the IRO. So, this demonstrates the importance of intensifier and bandpass filter for the chemiluminescence imaging. Thank you for joining us in this lab demonstration. We hope you find this session informative and valuable for your research and experiments in combustion and flame dynamics.